So the talk is, can we make elephants fly? And what we're going to be talking about is aerodynamics of jumbo jets. So we'll start with an elephant. This is an African elephant, weight 5,500 kilograms. It's got what we effectively see as wings, those big flaps on the side. So we'll call that the lifting surface area of its wings of 3.0 square metres. And when we measure its altitude above the ground, we find it 0. Now, I've seen a few elephants jump, but usually they jump with 1 foot on the ground, so they really don't get off the ground. The other elephant in the sky is the jumbo jet. Its weight is 400,000 kilograms. It uses a wing lifting area of 525 square metres, and it flies at an altitude of 11 kilometres. Now, what we want to work out is the difference. Why can't that African elephant fly when this massive elephant can fly? The first thing to do is look at some of the obvious parameters. Now, one parameter is wing loading, which is the weight of the elephant divided by its lifting area. Now, with the jumbo jet, it's 750 kilograms per square metre. With a standard elephant, it's around about 1,800. So we can see that weight over area is a bit lighter on jumbo. So maybe if what we do is we adapt the elephant, give it a bit more area, as per the Disney movie, maybe we can get this elephant to fly. That's a nice simplistic way of thinking about it. But what are the other parameters? What other things should we be looking at? So if we look in detail, we'll see, as we saw a minute ago, the wing loading. Elephants are a little bit heavy compared to the size of their lift capability, whereas jumbo jets are a bit lighter. The forward speed. Elephants run at around about 40 kilometres an hour. Jumbo jets fly at around about 950 kilometres an hour. Now that's a really big difference. So that's one parameter that is going to be very important to make a difference between elephants and jumbo jets. The propulsive power, one elephant power, I've estimated about 5 horsepower, whereas a jumbo jet's running at 140,000 horsepower in full flight. The fuel, elephants eat around about 300 kilograms of fuel, grass, every day. A jumbo jet, going on a half-day trip between Sydney and Los Angeles, in that half day it'll use 50% of its weight. So there's another really big difference. The value of the fuel, calorific value, the energy content of the fuel. Grass is about 16 megajoules per kilogram. Jet aviation, kerosene effectively, is about 46. So there's another difference. The structure. Elephants are made of skin and bone. Aircraft, aluminium, steel, composite materials. The strength is a little bit different. So aircraft strength, maximum tensile strength before it breaks, is around about 10 times that of skin and bone. So those are the complete set of parameters. And if we could adjust between elephants and jumbo jets, and we could get the elephant to go faster, we could have a lower wing loading, much higher speed, much higher propulsive power, and then use an excessive consumption of high energy content fuel, we could possibly get the elephant to fly. Okay, if we did, then we'd produce, to fly, the requirement that the lift produced equals the weight. So now we'll try and work out exactly how these jumbos get off the ground. Lift's got to be equal to weight. As we've seen, parameters, wing size, the wing loading, the amount of wing area required, and the speed. Now, one thing I haven't mentioned is the density of the air it's flying in. Elephants stay on the ground, whereas jumbo jets will regularly be up at about 11 kilometres. That means that the air is less dense, and that's an important parameter for producing lift. If we look in detail, the lift required to get one of these things off the ground is going to be some sort of constant in proportional to the air density. So the heavier the density, the more lift you'll get. The size of the vehicle, the more wing area, the more lift you'll get, and the velocity. And it's not just how fast you're going, it's the square of the velocity. So the faster you go, the big difference in lift. Now in maths terms, we can write that as L for lift equals a constant, which in traditional terms is called a lift coefficient. There's a half stuck in there. That'll get to later when we come to talk about Bernoulli and his ideas. The density is there, which is called rho, the velocity squared, and then the area of the vehicle. CL, in fact, though, is not really constant. You can actually change this constant by adjusting the way, the attitude of your wing to the airflow. So if we go and look at tests from wind tunnels, we'll find that if we change the attitude of the wing, if we change its angle to the flow, anywhere between 0 and 20 degrees, then we'll get changes in this lift coefficient constant. Typically it's linear. So we'll get, if we go from 2 degrees to 4 degrees, we'll get that linear improvement in lift coefficient. It's got an upper value. So when we look in the wind tunnel results, it doesn't just keep going. So by about 18 to 20 degrees, it's peaked, it's stopped, and it's coming back down again. And the other interesting point, it's not necessarily zero when you've got the wing lined up with the flow at 0 degrees. So these are properties of this constant which we'll need to look at a little bit more carefully. How do we find out what that constant is and how it changes? Well, we need to go back and look at how the flow goes. So in this case, I've got some real flow pictures. Now these, I'm going to put this note up on the side. These aren't just random sketches that people have done. So be very careful. If you go to look at computer animations on the web, you go and look at various sketches, be careful. Make sure that you look at actual flow pictures of real flow, because some of the lines, some of the flow patterns are very different from what people appear to see and what they sketch. So we've got a wing inside of an actual wind tunnel flow. We'll introduce smoke lines, and we can identify what's going on by looking at the visualization. Particularly, have a look at this middle picture. You'll see at an angle of attack, so we put the wing at incidence, the flow is actually changed. It's not just deflected, it's modified upstream around the aerofoil and then modified downstream. Now, from small angles to large angles, you'll see there's a modification to flow, hence we get that linear result, more lift coefficient for higher angles. The end result though, down the bottom, if we take the angle too far, the air tears off. It doesn't stay attached. It won't go around that corner, and then we lose our lift again. So we lose that attached flow and the appropriate lift. So if the angle's too high, flow will separate. And we'll come back, and if we get time, we'll have a look at the actual video. If you've got time, I've put it on the slide. It's actually on YouTube, so it's from University of Cambridge. You can have a good look and see how flows actually go. Okay, what are the mechanisms involved to make those flow patterns happen? Two things, Newton's laws and Bernoulli's principle. Not one or the other, but both at the same time. So Newton's laws require that for every action there's a reaction, and that can be written as briefly that you'll get forces producing accelerations for given masses. Now, we're not applying this to individual particles, we're applying it to a continuous fluid. So it's a little bit different than simple particle mechanics, but the effect is that the impact at the front of this aerofoil is transmitted upstream and it accelerates the flow particles around. Impact is transmitted by pressure waves. Collisions between molecules transmit upstream. Flow coming towards an aerofoil is pushed and produces accelerations. How those accelerations produce pressure changes, we rely on the Bernoulli principle. So if mass is conserved, so the flow coming along here can't disappear, it's got to be conserved. If its momentum is conserved, then there must be a change in pressure proportional to the velocity squared. So Bernoulli worked this one out. It's used in conjunction with Newton's laws. So both work together to produce changes in velocity, slow flow underneath, high speed over the top, and then subsequently, if the velocity is changing, going slower underneath, the pressure must increase. If the velocity is changing and getting faster over the top, then the pressure over the top will reduce. And you can see it in the diagram, that you can see the narrow lines, the increased velocity, you can see the lower pressure region. So as a result, fast flow over the top, low pressure, slow flow underneath, high pressure, that'll generate lift. Okay, again, just remember this is a combination. You can't do it with one or the other. You need both effects. Force, mass times acceleration, the reaction equals the action, plus you need the relationship between pressure and velocity to get the right flow. Okay, so we know the principle, we know the governing equations. How do we actually solve exactly what the velocities and pressures are? Now this is the hard bit. We can use all those rules to generate mathematics. Conservation of mass, conservation of momentum. There's a set of rates of change of velocities, Navier-Stokes. But this is getting very complicated. In fact, this leads us off on a different track into CFD, computational fluids, where you'll need a big computer to do the details. What we'll do instead is take an engineering approach. So we'll look at the flow, we'll test in wind tunnels what's going on, we'll see lift coefficient bearing versus angle, we'll see the effect of camber. So if I just line the aerofoil up with the flow, if it's curved, we still get that action upstream producing the flow, producing low and high pressure regions, and we get a lift value even though the angle is 0. And then we can see in the wind tunnel when we can go to a maximum where the flow tears off the front, it won't stay on there, and we'll get high pressure but no equivalent low pressure, therefore a loss in our maximum lift. So too much to do without a big computer. Engineering approach, measure it in the wind tunnel. If I put model of an aircraft in a wind tunnel, and I'm just going to warn you, this aircraft is big, you'll need a very big wind tunnel or a very big model, usually done overseas. But what we'll get are results. So we can actually measure in the wind tunnel the change in that coefficient versus the angle, and I'll get a nice little result where the lift coefficient is around about 0.1 per degree, plus an offset because of the angle of 0, the lift at 0.2. Okay, if we remember the original formula, then we can calculate our lift coefficient from the known angle. We can measure the aircraft, we know its area, we know its weight. Now, weight isn't actually in kilograms, that's its mass, so we'll have to convert that to newtons. We know where we want to fly, at what speed and what altitude. We know at that altitude of 11 kilometres, the air density has dropped down to about 0.3 kilograms a cubic metre. If we set an angle of attack about 4 degrees, put that into our formula, then use our basic definition of lift coefficient, half rho v squared area, so put the numbers in, then what we'll get is a lift at that altitude and that speed of around about 3.9 million newtons. Okay, the weight of the aircraft in newtons about 3.9 million. So with those parameters, those results, that jumbo jet will produce lift equals weight and will fly. Next problem. Now that's the first step. It's not just a matter of getting lift. To push the vehicle at 271 metres a second, you will need a lot of thrust, and that thrust must overcome the drag. Drag is not as simple as lift. Drag has components. Lift is pressure difference, top and bottom. Drag has pressure difference, but surface skin friction, so the air rubs along the surface as the aircraft moves, so we get skin friction effects as well. We get pressure differences from front and back. If we go fast enough, we start to compress the air due to our forward motion. These are separate lift components. And then there's a fourth one. Now this one is where the complexity starts. Generating lift generates drag. So there's an extra component, an extra penalty in producing lift which will add to our drag. All of that has to be overcome by the thrust of the engines. If I look at wind tunnel measurements again, so we won't go into complicated CFD equations and try and solve it directly, we'll go and get some wind tunnel results, and we'll find that versus airspeed, our drag tends to be high at low speed, minimises and then goes high again. Now this low speed drag is a complication due to producing lift. So if you can see it, down the bottom we have the wingtip. So we saw the previous diagrams of the high pressure underneath the aerofoil, the low pressure on top. Now that can't happen at a wingtip. There's nothing to stop the airflow moving around between the two regions. What will happen at the wingtip is the high pressure will bleed around to the low pressure, the air will start to spin, and trailing downstream will be a delicious trailing vortex. Now that vortex is producing drag. We need lift on the wing, but as a consequence the wingtip lets us down a bit and produces induced drag. When we look at the equations, we can see that we can produce a drag, which will be our constants, half and CD, drag coefficient, rho v squared s, as we had for the lift. Whereas in this case, because of these complexities, our drag coefficient will be made of two parts. First part we call base drag, made of the friction effect, the rubbing of the air on the surfaces, any pressure difference fore and aft, and any compressibility if we're going too fast. And then there will be a term of drag which is proportional to the lift, which is a constant times the lift coefficient squared, and that's due to these rotating tip vortices. Okay, we'll go through again just simply as an engineer would, take some measurements. If we put this in a compressible flow wind tunnel, we'll find that the base drag is about 0.03 at a Mach number, so that's 80% the speed of sound. These aircraft fly at quite high Mach numbers. We do our wind tunnel measurements and we find that this constant for our lift coefficient squared is around about 0.25. That means our full drag coefficient at our flying speed, our operating lift coefficient, with our equations, base drag plus induced drag is about 0.039. Then, if I put it into my standard formula for drag, coefficient, density, velocity squared area, put the numbers in, that means I have a drag of around about 275,000 newtons. Okay, now, can anybody remember what the lift was? How's that in proportion to lift? In fact, if you look at it, the lift was around about 3.9 million newtons. This is 275. Optimum streamlined shapes, we need our drag to be about the 10th the size of the lift. Otherwise, we get very inefficient vehicles, high fuel flow rates, very hard to go far. So this ratio of lift to drag is a very good measure of the efficiency of the aircraft. Most aircraft at this scale will be well above 1/10, up to 1/15, the ratio of lift to drag. So the drag will be 1/15 the lift. Okay, we've got this drag, 275,000 newtons. Therefore we need four of these things, four engines, to produce an equivalent thrust. An engine produces thrust, again, due to Newton's laws. Reaction equals action. In this case, what we're doing is getting thrust by having a very high speed exhaust flow coming out the back of the engine. And if I look at the simple balance, then the rate of change of mass out the back, the mass flow rate, times that exhaust velocity will be the momentum coming out the exhaust. That's the momentum part of it. The reaction to that will be the thrust produced by the engine. So that's a straight application of Newton's principles. This is a simplification. We'll go a little bit more detail on modern engines in a minute, but this is an original turbine type solution where it's just a pure jet. You suck the air in, you burn the fuel and you accelerate the flow out. Not very efficient. So in modern engines, what we'll see is that they have what is called bypass flow. So we've still got this initial principle where we'll have an intake, we'll have a compressor. So inside our core of the engine is a compressor that pulls the air in, pushes it to high pressure. So it's sucking it in, compressing it, ready to combust. We'll be injecting fuel in burners inside the main core of the engine. That's adding energy to the airflow. We make sure this is high pressure so the energy can't escape upstream, it's got to go out the back. And then what we'll find is that hot, high pressure gas will start to expand out the back through a nozzle and produce a very high core exhaust flow. Now that's good, except the high temperature core exhaust flow, that's energy lost. So efficiency is now gained by extracting energy from that hot gas as it goes through another turbine. So we have a first turbine which runs our compressor to keep it going. We'll have a second spool, a second turbine, which will run a large fan at the front, which will produce cold airflow around the side. So we're actually extracting some of the energy from that hot gas before it's exhausted to produce a cold gas stream. Cold gas streams are more efficient, they're higher density, therefore a bypass engine, a turbofan engine, will be much more efficient than a pure jet. Nowadays these bypass engines are running about 11 times to 1, the ratio of bypass flow to core flow, and that's very efficient. Now this is a little bit more complicated when I go to a bypass engine, because I've got two streams. So my thrust is now my mass flow, the change in momentum through the core, plus the bypass ratio times my mass flow, times the change in momentum of the bypass stream. So this is a little bit more complicated, but again, if we look at engine data, we can get results for the thrust. So m dot, mass flow through the core of the engine, beta times m dot, the bypass ratio, that's the amount of mass flow going through the bypass. And in fact, we're not just getting momentum of the exhaust, we are getting momentum of the exhaust compared to the momentum the stream already had. So it makes it a little bit more complicated. So we are changing the momentum of the airstream in our exhaust. Very tricky to scientifically predict what's going on, so again we'll go back and rely on manufacturer's data, engine testing. So this, for example, is the Rolls-Royce RB211, one of the most up-to-date, most efficient turbofan engines used on jumbo jets. The maximum static thrust it produces, so that's the basic Newton solution, is 270,000 newtons. Now that seems good, because remember, that's about the same as the drag, and we've got 4 of these, not just one of them, so we could say the thrust on the aircraft is 4 times that. Unfortunately, that is what happens at sea level on the ground. So when we look at manufacturer's data, we look at the operating point, which is our speed at around about Mach 0.8, at altitude of around about 11 kilometres, we find that because of the lower density of the air up there and the fact that we're going so fast, we're not getting the exact performance at sea level. Each engine only produces around about 87,000 newtons of thrust. But 4 engines, we have about 348,000 newtons total, which is more than enough to cover our 275, which means that the actual pilot can throttle back a bit and not use full thrust for cruise conditions at altitude. Okay, now that's lift equals weight, thrust equals drag. That is how a jumbo jet flies, except there are many more details to this. So we've just looked at the basic aerodynamics, but if you look in detail, wing lift isn't centered at the middle. Wing lift is centered on the center of the wing, so that there's differences between where the lift is and where the weight acts at the center of gravity of the aircraft. Thrust is not centered at the nose. Thrust is centered at the inside of the engines. So we have differences of where these things act, which will produce moments, and the drag doesn't necessarily act just uniformly at the front. It acts down the back, it acts on the wings. It's distributed. So we'll get complicated moments which need to be balanced out. That's a whole different new engineering area of analysis. But what we'll see is, for example, a lift here from the wing will produce a moment about the wing root where the wing is connected to the fuselage. The weight of the aircraft is basically in the centre, most of the weight's in here, so there'll be high stresses due to the moments at that point. So there are areas marked in red of very high stress on these aircraft, in which case that's the requirement for high strength materials. But this is getting away from aerodynamics and going on to lead to a whole completely new area. Okay, conclusion on aerodynamics, how to get jumbos to fly. Very simple. We have low wing loading, so we have a big wing area compared to the weight of the vehicle. We have high forward speeds to get the lift, which is proportional to v squared, sufficient to cover the weight. We have high power engines to cover the drag, which is involved, but unfortunately with gas turbine engines, they are a continuous combustion process. We need lots of fuel to power them. To get elephants to fly, I think what we need is a suitable padded container, keep them restrained happily in the cargo hold. The other way to make an elephant fly is with graphics. If you're on the internet, you can make anything fly. Just an ad for wildlife conservation, but with graphics, elephants can fly. So the internet is very good at having models of things which are impossible in the real world to actually work in the internet. So there's another nice example. You'll now see the exact flow over an aerofoil with measured airflow over an aerofoil. So you can see the curvature of the streams. If you watch closely, you'll see that the air moves slower underneath, faster over the top. So if they track in individual segments, the actual smoke, you'll see the smoke comes in all lined up, but then the smoke at the top moves faster, increased velocity over the top, the smoke at the top gets to the back before the smoke underneath. And then if we apply the Bernoulli principle, that means that the pressure over the top must be lower. Pressure is proportional to the inverse of velocity squared. The faster you go, the lower the pressure. We'll see the pattern change as we increase angle of attack. So at low angle you get just a residual bit of lift. Higher angle you'll see much more acceleration over the top, much more lift. It's effectively linear. But again, there's a limit to what you can do with air. It will eventually tear off the top, separate from the aerofoil, the lift will come down again. And with that big high pressure at the front, that produces a very big increase in drag. So attached flow at high angles, stalled flow at too high an angle. And even at zero angle, you'll see that the camber will produce curvature. That is a brief overview of how we can not get those fellows to fly, but how those jumbo jets actually fly. We've got plenty of time for questions. Mainly around the leading edge. So with a jumbo jet, where you're going incredibly fast, the air approaching the leading edge of the wings really can't go out of the way as quick as the air going around the fuselage. And what we'll get is an increase in density, a compression around the leading edge, particularly in near the centre. Now, if you've ever been in a jumbo jet and had a look out the wings, you may occasionally see little dancing waves across the top of the wing. That's the back of this compression region. Up the front around the nose again, you'll get compression. Air's being impacted really quickly by the front of that jet, and some of it can't get out the way quick enough, so it starts to get increased in density. Yes, but very small amount. Now the Russians have actually done experiments on this. The aim is to make the air hotter so the density in terms of friction is reduced. And the Russians did some very interesting experiments where they actually started to shoot very high power microwaves in front of their aircraft, and that reduced the density of the flow a little bit more, which makes it much more reduced friction. However, the power required to produce those microwaves is bigger than the reduction in drag. So it's an interesting phenomenon, but it's not efficient because you'll need more power to produce microwaves than you will to push the aircraft through the air. Very difficult question, very hard question. Jumbo jet development started in 1969 and has been improving step by step all the way. So aerodynamic improvement is at its peak. The big improvement areas at the moment are in terms of reducing weight. So you've heard of the new Dreamliner, where we're now replacing aluminium and steel components with composites, which are same strength but much lighter. And if the weight is lighter for the same size aircraft, the lift can be less, therefore that lift-induced drag component is less, therefore it's more efficient. Again, there are other options. The design of winglets to try and get rid of that lift-induced drag. There's a lot of research in that area. That again is something that still can be slightly improved. Possibly winglets which are not fixed but are actually articulated, so you can actually adjust the winglet to suit the flight condition, is probably one of the next improvements they'll make on the aerodynamics of jumbo jets. The aim of a winglet is to try and reduce the size of that rotation. So this is just a straight square tipped wing. This is a typical example of an inefficient wingtip. With the winglet, what you can try and do is adjust the angle of the winglet to reduce this spinning. This spinning is the thing that produces the extra drag component. So a winglet is designed to reduce the amount of spin, therefore to reduce the amount of tip vortex drag. For those who want much more details, much of this at a much more complicated level, I'm afraid, is on a site which is Aerodynamics for Students. And if we look at flow visualization here, we can have a quick look at a standard smoke tunnel visualization of the wingtip vortex. If you look carefully, you'll see the spinning of the flow off the wingtip. Again, these are actual measurements inside wind tunnels. We have smoke streamlines. You can see the size of the rotation, so that's a very big influence on the flow, quite a large component of drag. At high angles, that component of drag is as big, if not bigger, than the friction drag over the wing itself. The ultimate case is where you have the Concorde type wing, where those vortices are absolutely enormous, produce great big spirals over the top of the wing. And we'll have a look in a minute, you'll see a front view. So you can see the size of the rotations that producing lift creates in the airflow. Very large vortices, very large amount of drag. You may have seen prop fans, in other words, having external propellers on the back of these gas turbines. That has been a new area of research. It's been rather limited. Main research, again, is in actually material properties inside the engine. In terms of these, the efficiency is gained by very much mechanical means. So what they've been doing is adding more turbines and compressors to make this efficient. These components spin at different RPM. They're not as efficient if you only have two of them. If you have three or four, it's like gears in your car. It's not efficient to have 2 gears. It's much more efficient to have 5 gears. So more development in that area, in the mechanics of the inside of the engine to reduce mechanical efficiency. And again, the most development is going on with these fans to make them lighter. improve flow quality and make the bypass flow bigger. So bigger than even 11 to 1, maybe 12, 13 to 1 bypass ratios. Thank you.